Dude, I don't know what you're referencing, Omnivore. Are you in here? Like, you didn't reference a thing. You just started asking me a question.
So I think I understand the theory that I can see for the undiscovered secret sauce here is that I have a range of vision that's limited to 4,000 miles,
Ah,
basically.
ah.
Okay.
You've seen this go the other way. I remember now.
Well,
Right. So,
so what I feel like is that if I see Polaris getting closer and closer, it should be getting bigger and bigger.
well, you would think that if the distance between you and the object was changing as it was, parading through your vision, right? But if it was actually kept at the same distance optically, then it would make sense that it wouldn't happen. It does change aperture usually, so it's kind of a weird thing anyway.
But the apparent height goes. I don't know what the minimum here is, but it seems to get several hundred miles closer according to this.
Several
At
hundred
50
miles closer,
at
indeed.
56 it's 3,200 miles. So between 90 and 56, it's gotten it looks like about 700 miles closer. Is that correct understanding? The apparent height, so it
Uh,
appears.
I'm not
I'm
quite
looking.
sure what you're looking at, but I mean, like,
CD. I'm
probably.
looking at column D. I'm looking at column D. Well, I think it's column D,
Okay.
and the top is apparent height 3959. Right, that's as far away. So Polaris appears right on the edge of my vision. Like I can barely see it or whatever. I see it directly above me, and it's as far. It appears to be as far away as it ever gets.
That sounds correct.
Okay, so then I go down to 56 apparent angle, and the apparent height of Polaris is now 3282. So that's like 700 miles closer, or thereabouts.
Right. So, like, when we have an expression that would display distance when we're trying to do like an elevation angle, and we say that it's a linear relationship, we expect that to be linear the whole way, right?
It's the cosine, right? Or the so the it's the arctan, isn't it? Like what
Is that what you use?
I I'm not sure exactly what the question is, but if the baseline is my length and the angle of elevation, then the height is isn't it the arctan of the elevation angle?
I mean, like, I'm just trying to figure out when you're trying to do a basic elevation angle to a star and compute distance, right?
Oh no, I was doing trigonometry to tell how high something was.
Right.
So
But
I don't think that there is an apparent height when I'm looking at a angle to the star. I don't believe there's ever an apparent height because it always looks the same.
well, I mean, see, that's tricky for you because you have to simultaneously treat them as a static moving web equidistant from you at all times, rotating like a personal sphere, and then also believe that they're different speeds, different heights, all the way different distances from you, that different length because you did spectroscopy that can't be verified to tell you that it's definitely made of the stuff that's made in the sky, but you definitely can't know for sure. However,
I get the spiel. I understand the spiel.
do you though? Because do you think I like practice that?
It seems like it.
Come on, man. You think I would practice stuff for online people?
I feel like you would practice it and say it as fast as you could, and maybe hopefully hopefully baffle them. But I don't know.
Well,
But
the reason you say it fast is because you're gonna forget it, especially when you make it up every time on the spot, right?
yeah, okay. Well, anyway, I understand that you have a lot of questions about where the stars are, and that's fine. But I don't think I would be saying it apparently gets closer as my angle decreases.
Well, I mean, I would agree with you. However, that's exactly how NASA treats the sky and the dome and the celestial objects when they talk about them. So, like, of course, because you don't ever actually have a physical object, you have the apparent, as we explained. Hold on, let's get sources.
Well, wait a minute. Are you talking about the
No
apparent
sources.
height above the horizon, or are you talking about the apparent height above the observer?
Well, I'm talking about the very thing that you were about to ridicule and criticize is going to
Well,
be shown to you as exactly the model that NASA used, almost like it was premeditated. And it's nothing against you, man.
okay. So I'm just saying that apparent height is how it appears to me,
Right.
right? I'm the guy who's standing on the North Pole. I don't
Absolutely.
think that I don't think that I'm looking at that star and saying that looks like it's 3,900 miles away. I don't.
Right. Well, I mean, we kind of skipped to the end of this argument, but the premise, right, is that we have a fundamental disagreement about what causes those things to process into the distance proportionate with distance, right? Like we think that it's the same for everything on Earth because it looks the same and does the same thing. You think it's the same for most things except for the sky, which does it exactly the same for a different reason. It's a little bit truncated, but that's pretty much the position.
Yeah, I mean, I agree. I think the stars are a long way away.
Right.
But I what I don't think is that on either flat or globe Earth, the star appears to come closer, which would mean, as far as I can tell, it would get bigger.
Right, but like, so here's my actual position, right? Is like that you would see and experience the celestial sky exactly as you do right now, and it would be for a completely different mechanism because I'm just explaining how you see differently than you already do. You think that everyone can see the same sky at all times, but in reality, everyone sees a different sky, and you have no way to disprove it because everyone just looks at freaking NASA and we look through stellarium that has the same view all the time.
Yeah,
But
but I
all
mean,
of those are viewer dependent. All of them are viewer dependent.
but isn't this kind of like saying, I don't think you all see the same color red as me?
No, I don't think so because to a point we can track it, right? And then
Okay.
to a point it doesn't matter. But like,
Well, so
so this whole position comes down to, can we celestially navigate by looking at the things in the sky? And it has to be yes, because
right.
you treat them exactly as we treat them for the static moving thing, equidistant from each other as they process over you. And because we did a tricky thing with a unit circle to enforce a viewing radius, we then can say that actually mathematically, if we process laterally 69.07 miles, then yeah, this personal celestial sphere that I defined mathematically with basic trig will process over me 1 degree as I go. So that is definitely a relationship I can have. Now it doesn't maintain linearity all the way, but that's okay. That's what we're going for.
That spiel I don't understand.
All right.
I didn't quite get that. But what I did understand of it is, so we all agree that we can navigate the stars.
I certainly can.
And obviously, clearly, we can. So the I guess that what you're trying to establish is, you know, because of something about the way we see, we see Polaris drop 1 degree per 69 nautical miles.
Yeah, not only we, but everyone always has forever into perpetuity. You can say that.
Sure, sure. We all agree, right? So that's what we see. That's what we observe. So the question then becomes why. Now, when you say we don't all see the same sky, are you saying that we're not all looking at the same thing and just seeing it differently, or are you saying that we're literally seeing a different thing each person? Like if I'm standing 10 feet from you and we both look up, we're each seeing a different actual thing.
I'm
Like,
saying very specifically, right, that we can all see the same thing apparently, and no one ever sees it physically. You're concerned with physically, but again, pointing out that it's all treated as the same equidistant web until the point where you get right next to them. And as you correctly pointed out, right when we started, you put it at under 90, it goes right to almost infinity, meaning that like your distance isn't really real because it doesn't go to a scaled thing that's proportionate to all the web that's equidistant. It goes with light speed to each different independent thing, where however far you think it is based on that
okay,
ridiculously
so
skewed luminosity thing on the basic on the candle in the inverse square law of light.
so the theory is there is no real thing,
No,
or
no,
at
no.
least if there is a real thing, we're not seeing it.
No, the statement is the apparent is all we ever see. So this is all we ever need to deal with. Like this ridiculous how to justify like if you want to like get to under a star and take a ruler and try to reach it, that's stupid in both worlds, and I don't understand why we try.
Um,
This is what Rupert always says when we get to this point. Sorry. He's like, take a yardstick. It's 39.59. You go and do stuff. Can you reach up and touch it? Like, well, no, because I don't think it's like even there. I think it's a light in the sky that moves equidistant with movement. So
okay, so if you and I are both looking up, let's say we're 10 feet apart, and we're both looking up. Now I agree, although it's trivial, right, to say we each have a different point of view. If we're both looking at the Empire State Building
no,
and we're
we're not.
standing 10 feet apart, the building is going to appear slightly different to each of us.
There you go.
Yeah, I agree, but I think that's a trivial statement. We still both agree we're looking at the same physical thing. We're seeing the actual building. There's actually a building. There's actually a fact of the matter, and we're both seeing it. We're just seeing it slightly differently
Okay,
from
let's
different
check this
angles.
out. Here's this celestial sphere, which you have to use to look at the sky or do anything and mark a right attention there. Communicate to another human being where anything in the sky is. So I'm gonna stop right there so I don't talk too fast.
Mm-hmm.
Right, that's cool. That's a nice little observation. I actually put a couple of them together. That's going to be most of the observations that we run through as we go
Okay.
through. Right, so that's just basically how everyone sees the sky. It's literally in a sphere around you that moves with you. You think that it moves with you because of the curvature you can't see. That's always just outside your vision. I think it's because of other reasons that make more sense, but we're not going to go into that, right?
Okay. Well, we know we don't need to. So you have an actual Polaris, and okay, so you have an actual Polaris and an apparent Polaris.
All right, because Gleam kept showing it to people, and they took it offline, so now it's only on archive, which we had to pull it from.
Okay.
Also, all this is on this webpage that I keep publishing and using
Yeah.
reference things. Everyone
All
can look
right.
at it.
Okay.
So it's literally NASA saying that, hey, this is a supermoon, but it's because we perceive the sky as a flattened dome, with the zenith nearby and the horizon far away. We have birds flying overhead, and it's closer than birds on the horizon. When the moon is near the horizon, your brain, trained by watching bird, miscalculates the moon's true distance and size, giving you this wonderful flattened dome of apparent and actual. So, like, we don't need to go any further than that
Can you
because all
post?
we
Can
ever
you post?
see.
Can you post that?
Oh
Whatever it
crap!
was. I see the
Nah.
I see the picture of the flattened sky, but I didn't. Maybe
All
it's
right.
shaped sky. He sees the sky as a flattened dome. I don't know about flattened, but oh, okay. The true sky and the flattened sky. I see what they mean. The zenith near the horizon, far away. Birds overhead are closer than birds of the horizon. When the moon is near the horizon. Okay, so
Yeah, I was very slow against getting that. Sorry.
all right, that's fine. I agree that the sky looks pretty dome shaped.
I mean, like everyone does. Like it's the thing. And people start disagreeing. I'm like, well, hold up. Let's start like with. I think that when you look at the sky, it looks exactly like you think it does, and then we'll go from there because they think this crazy nonsense stuff where we have to get off the table.
Well, what I'm trying to figure out is you're saying that something is going on with vision, right? That there's something about our vision can only go 4,000 miles. I don't understand that. Um, but I mean, yeah, maybe our vision can only go 4,000 miles, but I think we clearly see more than 4,000 miles when we see stars, right? So right there, I would disagree with that assertion. But I'm not. What's that?
Sort of.
Okay. Well, I mean, I don't think it's true, but then again, I also think that the stars that make up what we call Polaris is in an actual place.
Right, but that no one ever sees
So
that you treat equidistantly like we do all the time. But I know.
yeah, well, yeah, I mean, and I'm well, but
It's a weird position, right? You have to use it exactly like we do, but say it's something totally different. That's twice now, right?
I'm restraining myself from applying the same mode of communication to you.
Okay.
I
Honestly,
can,
man, I enjoy
I can,
talking to you, Carnivore. You're one of the more honest believers.
okay, but I mean, I'm the idea that we do the same thing but have different theories to me sounds like saying, well, you guys figured out something that works and we're trying to copy it or we're trying to explain it.
I feel you. That's a logical stance to have. However, like the whole predicament that we're in is that everything has been taken away back within the internet and made exclusive against us. For example, right, since you bring it up, this exact measurement and connection with relationship to the stars, right? They said that this was specifically because of curvature and couldn't possibly be for anything else, even though they were wildly invoking it specifically only for this, while the same effect was being simultaneously explained perfectly well with distance and perspective everywhere else. So that was a predicament to have. However, no one can really admit this. Like this is where Bacon just like disagreed, and I was like, dude, I get it because this is where we have to part ways. Like if you can't we can't agree on this because otherwise the debate is over. If you agree that perspective is causing the stars to think, then the whole curvature is gone. Not to mention the specific derivation from optics that we have currently. So there's very limiting options for curvature. It has to be physical or to a higher degree of specificity than ninth decimal. So I don't know.
Okay. Yeah. So I haven't looked at, I don't understand the math to the ninth decimal place. I understand that that's your,
I think.
your math here, but that's an assertion that I don't fully get.
Right.
But what I'm trying to figure out here is if the attempt is to reverse engineer this stuff, to say, okay, so the globe says that the drop, that the reason we can't see Polaris from south of the equator for the most part is because it's blocked by the Earth, right? That's what the globe model says.
Specifically, right, exactly for that situation, if you have a way to describe the distance linearly, which is all that you have, and that observation goes below the equator, just 1 degree, without refraction, dude, how would that mathematically describe it?
I don't understand the question.
Well, if you can literally like scale distance and it's linearly based, and you see it past the equator, south of the equator, how would that function describe the distance of that star? Would it be longer than you could possibly describe it linearly, or would it go like I don't know, inverse or negative, or break, or what do you think?
I think I would be seeing through. I wouldn't be any much further away. I'd just be seeing through the Earth with like X-ray vision or something.
Right, that's fair enough. He's like, obviously, I would just be breaking all the rules because that's what I'm seeing. I love it. It's perfect.
Yeah.
Yeah, no, it's I
Right.
do.
Well, I think on the other hand, I also believe in refraction. So,
Right, right,
but
right, right.
for the most part, you can't see it.
So like, but
You
like, if you had an actual function that described that like towards like a bending towards a limit but never approaching it, sort of like a logarithmic function, wouldn't that better describe that relationship instead of linearly? because it would in fact be linear in all the times that you use it for linear, and then also describe the extremes which you wouldn't be able to.
So I don't know. I don't know about that. So that's not. I'm not clear on why a logarithmic description would be better. If I can't see, if we accept that for the most part, I can't see Polaris from 3 degrees south of the equator.
Yeah,
Okay.
honestly, I don't think that we can even see it. Like, I don't even think that's possible for anyone. So I was just like hypothetically
Correct. I
proposing it
agree.
anyway.
Well,
Okay,
I
yeah, cool.
agree. I agree. But doesn't your theory suggest that if we put a powerful enough telescope 3 degrees south of the equator, we would be able to resolve Polaris?
No, no, I'm specifically arguing that, like, at the horizon, at the surface level, that 3 mile horizon is very finically dependent on the specific aperture of your eye, the focal point you're looking at, and the aperture of the wavelength. So, like, it could change at any moment and probably is pretty variable. So, what happens is it's constantly dynamically scaling, and that literally determines just like the spherical radius. So, the spherical radius is applying to the celestial heaven, which you have quite a bit distance of seeing. You're not going to be seeing 3 miles into the celestial heaven, or 4,000 miles into the atmosphere, right?
Well, I don't know. If I have a telescope and I'm
Right.
not looking through it with my eye, I'm looking through. I'm projecting it onto a photographic plate.
Okay.
Then it seems to me that if there's not a literal physical obstruction between me being south of the equator and Polaris, and the reason why it seems to drop is because of something going on in the curvature of my eye that is not going on in the telescope.
Well,
That
was
Mhm.
there more?
Well, that I would be that I would be able to resolve. It's the same thing with the sun being a sphere that flies away at night. It gets too far away for me to see, and then I can't resolve it, and I think it's set because of some reason.
Well, similar but slightly different, right? Because when we're on the horizon, it's slightly different. We keep mixing up the two. If something is unresolvable, it just means that it's gone beyond my current aperture length to resolve it. Doesn't mean it's gone, I can't see. It's beyond 3.1 miles, let's say, beyond what I can see currently. If I stand up or do anything else, that'll change all the conditions and have to scale dynamically. If I move to a camera, that'll change both the wavelength inserted at the beginning of the Rayleigh criterion and the diameter accordingly. Now, that would also scale what we're doing with the backwards compatible ratio, defying wonderfully spherically distance defying limit of the tangent of how we get the arc length of the sphere. Dude, that
Yeah.
was really off the
So
top of my head. Sorry, honestly.
no, that I follow that. Right. I understand what you're saying. Yeah. Obviously, that stuff will change if I, but that still tells me that I should be able to have a powerful telescope like the one that well, not super powerful telescope, but a good civilian telescope.
Yep.
South of the equator at roughly sea level, and be able to see Polaris.
Um, I mean, I don't think you'll be able to. What do you mean?
Why not? So why wouldn't I be able to see Polaris?
Well, I mean, I wouldn't be able to with the way that I understand the world to work because I'd be like far enough away from that center to not be able to see it on my horizon. And even with the
Yeah,
nonlinear
but
function describing it, it wouldn't be that, I wouldn't be able to resolve it past
well,
these
but I've got a
scalings and
telescope.
infinity.
I've got a telescope, that can resolve Jupiter and show things that look like craters on the moon and stuff like that. So I've got a great telescope.
Well, a
So,
telescope doesn't make anything that you can't see visible. It just brings things that aren't currently resolvable into your range to resolve them, right? That's clearly
right.
exactly what it does.
Yeah, I agree. So why isn't it why isn't it visible from the equator? What is
But
stopping it from being visible from
well,
the
it
equator?
can't ever go past that limit. So no matter what scope you have, you're never going to be able to see past your limit of like into the sky, right? You're not going to be able to see. For you, it'd be like seeing over the curve real quick. You put in this like the stethoscope over there. That wouldn't make any sense.
So that's not. So it's not a range of human vision. It's like a range of.
Well, it's absolutely that, right?
Well, then the telescope has nothing to do with human vision.
Well, I mean, like if you see everything as one, then eventually you have a limit to the vision of whatever aperture, scope, vision lens you're looking through, and you have this effective either dome or scaling horizon limit that just happens to happen every time without exception.
Yeah, when the things converge in the distance, they don't do it in a linear fashion. So once you hit a certain convergence point of things converging in the distance, no amount of optics is going to bring it back into view because the angle is too sharp that you're never going to be able to resolve the difference between the ground and the sky.
Oh, that's the other part, right? I'm tired.
So, say that again.
Yeah, it basically just as like the star is disappearing into the distance. Let's say you're going south and Polaris is sinking, right? Once you hit a certain point, once Polaris has sunk to a certain point, it's not going to be resolvable anymore, not because it's so far away, but because it's so close to your horizon that the angle there is so like it's not linear. It's not linear. So like you could have a really really strong telescope, but it's not. It needs to be an order of magnitude stronger because the relationship of the way that Polaris sank into the horizon and converged into the horizon, it's not a linear relationship. Once it hits a certain point, the angle is so sharp that like any amount of optics isn't going to bring it back into view because the angle is so sharp that you can't differentiate between the sky and the ground. It's just a matter of convergence when something's that far away and that close to something else.
Well, so first off, we think it's 4,000 miles away, right?
We do.
The theory here is that it's 4,000 miles.
I mean, at least we can say the very good, very substantiated, mathematically, logically cohesive theory, right?
So what I'm trying to do is think of a way to test this. So I don't understand the nonlinear. You're saying that as I increase my distance, the amount that it drops is reduced actually in terms of angle.
Well, but the problem is, right? Like, it's not about the distance. What it's about is, okay. So you're saying it would reduce in distance. I mean, it doesn't really matter. Like, the point is what you're able to resolve, right? So even if the angle change is reducing, that's not what's causing you to lose your resolution. What's causing your ability to resolve the one object from the other is the way that they've converged into each other, and that's dependent on specifically where that angular point. And once you hit that angular point, like I said, the resolution.
What do you mean by
right
angular
there,
point? Are you telling? Okay, so general perspective.
I'm talking about the point. Sorry. I'm talking about the point where, as you're starting to back away, like once you hit a specific angle limit, like no amount of optics is going to be able to bring it back into view because it's not a linear thing where it's like, I can see these two objects, and then now they've converged, and then I can just bring it back in with optics because you're actually the angle there is so sharp and the distance is so far that you're bringing that resolution back in isn't going to matter because those two items are so close together from your perspective point that there's no way you're ever going to be able to pull them out of their convergence optically. You're going to always see them converged in the distance because that angle is too fine.
So I don't understand I understand what you're asserting, but what is that based on? I don't think
here with this meme, it's perfect. It's everything we need to understand. It's the horizon drop distance, the spherical arc to get the arc tangent, and then the actual limit with the resolvability total. But
as far as I understand it, perspective squishes everything from all directions, up, down, left, right. But it doesn't make things. But the newly added conjecture is that it makes things also drop in our visual space, not just from being squished, but an additional effect where it drops due to some kind of optical perspective that matches what we'd expect from Earth curve. So we see the peak of the mountain not only get squished but also drop, and that is something that we have yet to verify.
So let's think about this for like 1 second, right? We've already clearly proven that there's an optical effect happening when you look at things and you look at things at distance. There's a definite atmospheric effect. There's a whole bunch of things going on. Definitely have an issue, but you've decided that you're going to not incorporate any of that.
I think that the thing to do would be to show that amount of drop in a testable, just to say, okay, now you don't think that this is do you think that this drop is because of the human eye?
I think it's an optical effect that scales covariantly with this wonderful triumvirate of equality that I've discovered that I'm going to keep using when people are back and forth.
Okay, well, if
part of it's optics, but then part of it's angular resolution, which is tied into optics, but it's a different. It's not the same function, right? It's going to have a different relationship with distance.
But it's like so far optics that it can't be physical.
Optical resolution is something that I can, correct for. If I think I can't see this anymore, I can correct for it by having a bigger aperture, a telescope, whatever.
Yes, indeed. Here, let me give you my spreadsheet where you can make all those changes and test everything you like I did. It's pretty fun.
Okay. So I don't think angular resolution could play into it.
Absolutely.
But the key, but the globe understands angular resolution as well.
No, see, that's the thing, because you don't at all, you've never applied it to anything, and we clearly know it exists, and you've only attributed it to curvature. So, the real question at this point is, have you ever seen curvature and angular resolution in the same place at the same time? Or is it like the flu that mysteriously turned into COVID a little while ago? You know what I mean?
Maybe I don't know what angular resolution is. My understanding of angular resolution is the limit between as something becomes smaller in angular distance, right? The angular size of it gets smaller and smaller. At some point, I can no longer see it.
Yep.
but I can bring it back. I can bring it back with a telescope.
Yeah, you could change the resolvability limit that you have thoroughly, bring it beyond the threshold,
Right.
making it resolvable once again. Absolutely cool.
So I think we have used angular resolution everywhere in distance model
In fact, curvature debates specifically, right?
Well, no, when I'm looking at a peak of a mountain through a theodolite.
Sounds like a curvature debate already.
Yeah, well, it is, but not necessarily a debate yet. I am using a magnifying function to make sure that it is resolvable. But resolvable is like a yes/no question, or with a very thin gradient of maybe. Right? Yep. I think I can
changes quickly. Yeah, I would assume.
Well, yeah, but but we're up in the altitude, so we don't see a lot of refraction probably.
Why you choose a red-orange wavelength specifically, right?
Yeah, well, whatever. But I mean, I'm looking at a peak, and I see that it gets smaller because of perspective, but I can still resolve it. Right? There's no question about me resolving it. I can see my crosshairs right on it. Okay. So, but it still seems to be lower than I would expect. Our two peaks are the same height, the same elevation, are measured at the same elevation, but it appears lower. It's distance away. I attribute that to Earth curve. You attribute that to something else, but it can't be angular resolution because I can resolve the thing. So if it is due to one more thing, let me finish. If it is due to angular resolution, I think it's due to some method of angular resolution that either hasn't been discovered yet by the mainstream or that we're not going to agree. Basically, I think it's a new thing. You're saying that there's this new thing about angular resolution that makes it drop. Go ahead.
But yeah, no, so it's not all that. It's essentially a couple things, right? You have your resolution limit being unresolvable, playing a role. The larger role you have is playing this horizon distance, top and bottom thing. It's like this: the bottom disappearance is literally mandated geometrically by how you see in perspective. If you're looking down a hallway, it naturally has to literally becomes unresolvable quicker because of the angle coming in at the light of the lower horizon. It just becomes unresolvable, literally into the angular resolution threshold. It become unresolvable quicker than anything that it could approach it. Literally, like all the gifts that I'm putting in here right now are all about the distance to the top and the bottom. And like the easier question is why does it disappear top down is because that's a huge ridiculous distance away. Of course, proportionally it would have to go bottom up. And then you're left with as it goes in the distance, you have this drop rate that seems to appear optically, which we've derived and commonly known as 8 inches per mile squared. That wonderful non-linear, now I'm gonna say non-physical function, which will describe, say, the optical drop rate that you so nicely observed to put right in my basket of proof, since I'm going to claim all optic measurements of curvature going forward with wonderful math to back it up, and physical curvature has never been substantiated. So,
okay, so the theory. So just so I understand this,
yep,
and I guess maybe this is to Toby. Are you claiming that there is some undiscovered method of something to do with optics that makes the things appear lower? Do I have that correctly?
I would say it's not undiscovered. I think pretty sure we're aware of the non-linear relationship in certain zones of the azimuthal grid.
Dude, 8 inches per mile squared is like a tenet of this engagement between each other. I think both sides agreed about it forever. I don't know why we would disagree to 8 inches per mile squared, but whatever.
Well, I agree with 8 inches per mile squared. I agree with that. But what I'm saying is I'm not aware of an optical effect that would make that happen. That would make the peak is fully resolvable. It's squished by perspective. We don't have atmospheric, refraction or other things going on, but yet it appears thousands of feet lower because.
Okay, so if you have let's say you have two parallel boards, or maybe say two sticks, right? And you start walking away from me with those two sticks, holding them horizontally. At some point, those two sticks are going to look like one stick, and then at some point, going to look like no stick. And that's the convergence that I'm talking about. And
yeah, but
at no point, hold on, Omni. But at no point is the stick going to drop. If it's above your horizontal, the stick's never going to drop below your horizontal line.
But it'll converge into it.
But it'll never drop below it. And Omni's telling you we're seeing things below the horizontal, 8 inches per mile squared.
Oh, see, I must have missed that.
Well, it appears it's not that we're seeing it underneath the horizon. It's that right? Jeremy's right. It's that it appeared the whole image of the far peak seems shifted downwards by 8 inches per mile squared. I put a picture of a hallway in there, and it gets smaller.
That's still just angular resolution. I mean, the peak of the mountain is going to be lower because the angle's different. You know that.
The horizon compresses and drops
No,
optically.
I don't. I don't think I know that. No.
Hold on,
Well,
Omni.
just
What were you
it's
saying,
just
Shane?
yeah.
Hold
Go
on.
ahead, Shane.
What did you say, Shane?
Well, yeah, so we'd have to say that it would disappear from the bottom up at the expected optical rate derived from the 8 inches per mile squared, right?
Well, I'm
but
assuming in
what's
real life
causing
I
it?
can't see the bottom. There's other mountains and stuff in there, but I can see the peak.
Yeah, but what's causing this thing to drop below the horizontal? Like that's, you know what I'm
Well,
saying?
I mean,
I'm
like
gonna have to.
you know how we have a sunset every day that like seems to go into the thing where people used to say it had portals or thing, or like you know how when everything goes away from you, you can't see it anymore, or like how the stars process from one horizon and go to east to the west. I mean,
Yes, because they're dropping below your horizontal line. Yes.
Yeah, can I
What
maybe
causes
give
that?
I was going to give an example earlier of like, the resolution on your monitor. You can't just keep opening windows on your monitor. You have to keep, if you want to open another window, you have to shrink down your other window. And if you keep opening more and more windows and keep shrinking down the other ones, eventually you're going to get down to the size of 1 pixel. And then if you try to shrink it more, once you get past a certain point on that 1 pixel, you have now gone down to 0 pixels. You've gone past the point of resolvability. It no longer fits into your resolution. And that point, once you're past that point, and if you go past that point in a nonlinear fashion, then pulling something out of that point using optics is never going to work because you're so far beyond angular resolution. We don't have instruments that can pull something back into resolution at that rate. But then regarding the mountain, that's just distance. You think about it, like as you move away from that mountain, your angle from you to the top of that mountain is going to change, and the top of that mountain is going to appear lower. I mean, that's simple perspective. Sixth grade train tracks converging in the distance.
No, that's not simple perspective. You ever see a perspective grid?
are you
But
applying
I'm
unlimited
saying
spherical space derived
That's the
optically from
opposite of simple.
vision?
You like made something up right there. I've never seen something on a perspective grid go below horizontal.
what
Well,
what
man, have you been applying like this wonderful spherical limit of vision using in the R10 to get the distance to make it match to the radius exactly, or have you been doing something different?
Sorry, say that again.
Right. So, like when you happen to apply optics, are you applying a limit to the vision that you have that's in a spherical fashion in any way, or are you just assuming like them that you can linearly scale your distance forever and infinitely?
I don't know. We see in a sphere, yes.
Right. But like, do you
Then
think
what?
that you can see lights from 1,000 galaxies away that are travel 1 billion years? That means that they're from 13 billion years ago or whatever.
Bro, this is like a building on Earth or a mountain or
Right,
something.
right. Just making sure. So like, but we don't blitz. So we don't need to scale linearly infinitely into the future. We know that we can only see a certain rate, and then it has like a distance at which it would become unresolvable, or like the good old distance to horizon like equation, right?
You get things get farther away, they get unresolvable, yes. But how does that
Yep.
account for them dropping below the horizontal line?
Well, it doesn't. That's something different entirely, right? So we're going to combine those two things specifically. We're going to say it's becoming unresolvable, and at the same time decreasing optically, bottom up due to this wonderful limit of now, like I said, optic describing this inches per mile squared function, which will be essentially a parabola, but at this distance, the expected optical drop off rate, which we only ever find optically all the time, it seems, right?
Yeah, but I'm saying though, what's causing the things to go below the horizontal line?
Well, I mean, like forever, everyone in the world has been watching this happen, right, and attributing it to different things and being crazy and having ideas. But like, honestly, it's only been found optically. You can't actually do anything about measuring it. It's only an
and
optical phenomenon, and now like the math specifically backs an optic derivation, like not two or three times. Like it seems almost certain that it's optically derived, not only like from the beginning, but all the way around.
yeah, and real quick, we don't witness anything going behind the horizon ever, never. That's not what we see. What we witness is things converging into the horizon. Every single example you've ever seen, that's all you've ever seen, is something converging into the horizon. You couldn't witness something going behind something else without using, like X-ray vision or something.
But so we should still be able to see this not in the horizon. Then, right? We should be able to simulate this with smaller objects and shorter distances, right?
Yeah, like kind of like how when you watch a car drive off, it gets smaller.
Sure. Well, I agree that it gets smaller. Everybody agrees that it gets smaller. I think that's
But it
a
doesn't get
given.
smaller in reality. That's the
No,
point. It's just
right, but it
appearing
doesn't
to
go. It doesn't get lower.
Okay, so you don't think that if you were standing on, you're standing, so you have a perfectly level plane, and that car drives off, and it keeps driving, and you just sit there and watch it and watch it and watch it. What do you think the top of that car is going to appear to do?
It's going to get squished. Same with the bottom.
It's going to squish
The
down
bottom-
into the horizon, and the
Well,
bottom's going to squish up into the horizon, the convergence point.
Right. They'll squish in all directions, but it
So
won't.
it'll appear as if it's curving down behind the horizon,
No, I do not think
but
so.
it's
No.
not actually. It's just converging into the horizon.
Well,
Yeah, I don't.
Just like
I
stick
don't-
to the 86 per mile squared. Everyone agrees to that already, no matter the model, right? That's the baseline.
Right, we agree to it as an approximation, but the actual amount of drop is more
Parabolic.
complicated. Yeah,
Parabolic
based on the
per
curvature
mile
of the
per
Earth.
hour.
Yeah.
Yeah, the actual drop over distance is never measured.
Well, we can assert that it's never measured. I think it certainly has been measured.
With
Show
optics
it.
purely.
Well, I'm specifically asserting that right now. So that
I understand, and that's fine. You can say I don't believe your measurements. I could say I don't believe your measurements, although I'm not sure what they are. But I could say I don't believe your disbelief. But
Shane, you didn't provide this guy with your math yet, and your how you derived all this.
I've seen the math. I don't understand the math.
Gotcha. Okay.
And it's not because I don't know how to do math. I'm not clear on the math. Doesn't come with a white paper or something. A set of English readable instructions.
No. But like,
No,
hold on.
I know Shane's got it. I know Shane's got it. Yo,
Hold on,
you got
I was
some. You
petting my
got some
dog.
explainers.
And I came over here and he kept the thing, so I unplugged the whole thing. So like, we started by going over the math specifically, did we not?
Kind of.
Exactly, specifically,
But
explicitly or kind of.
well, I was looking at your spreadsheet and I was trying to figure out, when you're talking about the first thing that I questioned was in your spreadsheet, you had Polaris getting closer and closer or whatever.
Right. So this was to specifically justify that 39.59 limit that I enforced on the whole thing from the beginning.
Yeah, but you have apparent height. So that means at 56 degrees, Polaris is like 700 miles, appears to be 700 miles closer to.
Appears to be, can be not in reality, right?
Right.
For sure, yeah.
Yeah, but so my first question is, does it appear to be 700 miles closer? I don't think it looks any closer at all.
That would be a point for me. That's exactly what we're arguing, right? It's literally doesn't appear, and it's equidistant from you the whole time. It's progressing laterally across it, moves the sphere up around you. It's perfect.
Okay. All right. So why does A, B, C, why does column D have apparent height in it? What does that mean then?
Well, it's to represent the exact spot where you would see it, as it would for everyone individually, as it's the only way to accurately represent it.
So it appears to be 700 miles down.
Well, I mean, remember when we started with the celestial sphere, and I said this is exactly how everyone sees when you need right attention and declination to tell another human being where anything is in the sky anywhere, right?
Yeah, I would expect to use angles.
Right. So what we have then is this spherical limit that you have around you that you experience every day, that I experience every day. That's exactly the same as you see it. That literally just moves with you, and that you think moves for curvature. That I think now have proved moves, for non-curvature reasons. Probably more logical, mathematically justify the reason that everything else does it. Probably, but now we have that same relationship on the sphere that explains reality better. So we've at least went through one hurdle, I think.
Well, not really. So what does the apparent height mean? Is that it's lower on the horizon, or does that mean it appears to actually be closer to me, or what do I make of apparent height and apparent length?
Sure. Do you want to see a model?
I'd like an explanation.
You want to see a model?
Yeah. Well, I have a feeling that the model is going to be another picture that I'm not going to be able to.
It's not. It's much worse than that.
Okay. Is this the Walter Bislin thing?
Model with we'll call it with a meme.
All right. Yeah, I've seen that page. I haven't seen that.
No way. This was around over the video. I'd never heard of it.
Also, Shane, look at what I posted at 11 minutes after the hour. It's an optics experiment I did.
I'm sure it's awesome. All right, hold on. I had an awesome meme that I want to just. Yeah, okay, there we go. Cool. Okay, I meant to put a thanks Walter link on here eventually, but I meant it to go with this though, since I don't think he's actually refuted any of the heliocentric stuff that I put out there in the first place to get him to admit to. Apparent versus actual, right? The big dispute.
Okay.
We're watching here. I remember, right? So the sun, as it comes in and approaches us, we see it rise. Oh, that's the wrong one. Hold on. Let's do this, and let's move. Over here, we have an actual sun that we don't see because we're in the dark over here in our little bubble, which is supposed to represent 3959, but is definitely not visually scaled to do so.
Mm-hmm.
Okay. So then when the sun approaches, as every person on Earth sees it, you get this rising thing that appears to rise, correspondingly the north of east and south of east in the north or south court, whatever is your invariant there, and then of course the inverse in the corresponding season, so that it gets this frowny happy face that you see, which we can just do I think right here real quick. We'll just get the daytime, so we see it, autumn, fall, summer, fall, cool. But let's do just basic like sunrise, right? So as it comes in, everyone sees it at its own little arc, and that's
So
exactly
I understand the idea that the sun is in a place and we see it in a different place. I have no problem with that. But what does apparent height, or what it was, apparent altitude? What does apparent height mean?
No, it's easy. It's what everyone it's what everyone does. Is what you have to do. It's what NASA does. Is what the way we represent it. Crap, I'm supposed to have the other model up so I can see that. Where's
I don't think NASA is giving things an apparent height. Are they?
Well, we started with that premise, right? And we then showed you the model from NASA that showed the exact apparent height for the moon description that we had to take down off the internet because Gleam was beating people over the head with it, right? We went there again. We can go there again because I do love it. Hold on.
I haven't. I don't. I mean, you showed me a small clip of a of a picture.
Okay. Well,
But,
also here's
okay.
this in case anyone wants to go through it. I mean, there's a little bit here.
Also, if it's evidence you took it down because of Gleam, that would be hilarious. I'd love to see that.
Well, I can't prove it. All I know is that it's not
Okay.
there anymore, and it's only on archive. So,
Okay.
however, I do like the story, and I'm going to keep saying it.
There doesn't have to be evidence, but if there was, I wanted to see it.
Well, if somebody wants to disprove it, I guess not. I can't. It's a really good story. Honestly, Gleam hasn't been wrong about anything, so I have no reason to distrust anything he says, man.
Okay.
Anyway, that's clearly what we're doing with Walter Bisland's model, right? We have a little celestial sphere. It's probably more accurately modeled by these little things that I just pulled right from Solarium, because again, it's exactly how you see it, and we see it the same all the time, right? It's just this right here. It's this dude, like walking, right? Like he just experiences things progressing as he moves laterally. That's the whole thing. That's the whole description. It should start with you should experience no changes if I'm exactly right about all this. That's the worst part.
Well, I don't. So the problem with reverse engineering is that it also doesn't make a case for it.
Makes a very strong mathematical case not yet put forth. What do you mean?
Well, okay. I mean,
It's not reverse engineering. It's just another theory, essentially another framework. But it's not reverse engineering. Reverse engineering would be
so. Let's do that then. Not reverse engineering would mean I start with my theory, and then I apply it to what I see. Right? I have a theory of how things should look that is created, and it doesn't say nothing should change.
So either you'd have to acknowledge it's a theory and that it's what Shane's doing is not reverse engineering because he's just deriving from the same things, or you'd have to say that it's not engineered, right? Like the whole thing is like it's semantics, but I would say that's not the proper term.
Well, so the way that we know that for a fact is there a place where we can apply this that is distinct from what the globe predicts?
The kicker is it's exactly how you would predict it everywhere all the time. So either I'm like all the right, or like we got to find some physical curvature.
Well, I think we found plenty of physical curvature, but you don't believe it, so.
Well, we find optical curvature, I think, right? Optics, a lot of optics. We got theodolites, we got optic measurements, we got that of a distance, we got spherical excess, we got all sorts of optic stuff, but very lacking on the physical. So,
well, I think we've also done plenty of physical as well, actually.
I came in kind of late. Shane, did you already go over how you derived everything, and that it's not from the globe, right? And you could reverse derive it with other variables, so it's not like
I thought so.
Like the idea that it's exclusive to the globe or like a reverse engineer of the globe. It's the opposite, is like what he's showing, because he derived it independently, or derived the radius independently using the Rayleigh criteria.
Yeah, more specifically, like the very specific starting parameters of the Rayleigh criterion that were tied specifically to the wavelength of, red and orange right here with no refraction and the human diameter of like 2.16 at the exact distance that you want to focus, which again, very fleeting and crazy. But if you're going to pick the variables that you want to best absolve, everyday reality, all your observations and the best mean average, then that's what you pick. And then it turns out like when you do that, that's when you get the radius backwards from the arc. Then you get to the 8 decimal.
I don't see how the Rayleigh criteria, I understand that that's how you did. You say that's how you did it, but I don't understand how you did that.
Okay. Well, so when we start with the Rayleigh criterion, right? Can you see this little tiny image over here?
Where? Are you showing it?
Yeah, I'm also putting it in chat.
Okay. I see a little tiny image.
So there's like a little Excel sheet in the bottom where obviously the wavelength and diameter is there as a variable that would enforce the rest of the things that are there, right?
I guess.
Well, I mean, you have to take my word for it because I could just be lying, right? But obviously, that's what I'm saying. It is. I could have manually written all those decimals there, I guess.
Okay, so the Rayleigh criteria, the angle is 1.22 wavelength over the aperture diameter.
Yep, that's the formula for it, right? So when you can choose the parameters, then yeah, you can choose the wavelength and the diameter.
Okay, so
Yeah,
yeah, okay. Mm-hmm.
But like the thing is, we can also get this value backwards if we have already the radius or the rate at which things appear to drop. And then we'll be able to resolve it or derive algebraically.
Okay, so let's keep taking me through that. So what wavelength am I looking at, and what's the aperture? So we're using the aperture of my eye, but let's say that we're using an aperture of a telescope.
Like you guys, I mean, like sure we can, but you guys always do this. You're like, let's see what it is at all, and I'm like, here's the perfect condition. And you're like, I don't like where this is going. So what we're gonna do is jump to like, what do I change everything all right? We're gonna go to the telescope. And it turns out,
Okay.
right? Turns out that's totally fine. It absolutely no problem. It just changes. Let's say the wavelength that we're gonna start with in the Rayleigh criterion to make things resolvable obviously will change, and the diameter with which we have the light to adjust will also change dynamically. And then of course we'll have a different, say, resolvability distance, which will dynamically scale with our viewing distance, and we'll be right back to where we started. But why don't we stick with the original scenario where we have the actual thing where we get to choose, the red and orange, which people in the chat say for is no reason. And again, let's reiterate very slowly, is the exact value of least refraction at the surface and is the representation of the mean average of all the data we could use.
Okay, so
when we take it forward just a little bit more, right, we have this value which we end up with a degree as a resolvability ratio, which just tells you the rate at which things can be unresolved, they become unresolvable, or when two things become unresolvable into one.
Okay, right. Okay, so I've got my 666, right?
Right, the wonderful devil numbers, right? But like,
Okay.
I didn't choose them for numerology.
That's fine. That's fine.
I'm like, hey, you know what works
I don't
best?
care
The
about
ones.
that. So what?
Cool.
And then 2.16.
Yep, exactly that number, exactly. And then we take those numbers and we go a little bit further. Try not to get. This is going to be a little bit. This is just the stuff we already agreed upon. Don't worry about that.
Mm-hmm.
So there's this one conclusion.
Okay, I can't read that at all. Okay, go zoom in. All right. So
All right, so from here you can probably figure it out, right? We're going to do. Actually, probably need a visual.
no. Let's go through the math. So okay, so I've got. So according to the Rayleigh criteria, the angle at which I can no longer do it is 1.22 is diameter of aperture, so divided by 1.22 or 1.22 times wavelength over diameter, right? So the diameter of the human eye is 2.16. What is that?
That's like squinting at the horizon at the least exposed aperture relating to the light versus dark ratio. 2 versus 4 to 4 versus 8 nanometers, I think, off the top of my head.
Nanometers or millimeters?
An M. Yeah.
So we've got 0.308. 33333.
Right. These are supposed to be the parameter that we just derived, right? We just got the.
And what is that in radians?
This is well, no.
Okay, what's it in?
Yeah, that's miles. So we got distance to the horizon basic formula, right, which we already agreed upon, derived from the ages per mile squared basis from which we engage, and then we're going to use simply that. And this is why I said we need a picture, right? Because I love this one. Because again, I don't know how else to use this unless you have like a spherical limit of vision. Can you see this whole picture now?
Kinda, yeah.
Great. So we're just going to assume, right, that at this ledge of our spherical vision, we're going to take an arc length. We're going to do a basic freak function, and we're going to get this amount right here, this bendy thing that we're going to call the outer edge of a spherical limit, right? So if we have a dome, like I've been saying.
So you're calculating the length of the arc.
Like this is the function that we're applying, like visually to the exact parameters over here to get this value, which everyone should Google and figure out if it's close to the radius or anything like that.
Well, hang on a second. So divided by the tangent. So what's the 2.999?
Distance to the horizon, miles.
Okay, so distance to the horizon is 2.999 miles. I got it. Okay, and then we're dividing that by the tangent of what? How did you define the angle there?
Which angle? Theta, right here. This one.
Yeah, whatever the angle. Yeah, that.
Which is the same thing over here, right here.
Okay. Yeah. How'd
Right.
you get that?
Right here. See, see how this is exactly this value right here. This is how exactly we define the angle.
So you got it from the 3 mile horizon
Yes.
divided by. Okay, hold on a second.
Don't go crazy, dog. You're fine. Let it go. I knew it.
So where do you get R from?
From that equation right there, that's what we're solving for, right? That's the variable. The
So
only
then
one.
how do you get the angle? You can't get the angle without R.
We had derived the angle already, right up here. When we check this angle over here, and we got this.
Wait,
Right
where
here.
did you
When we use
get
the 3 miles, when we assume the horizon distance, right? We start right over here.
Okay, so that gives you the distance, and then how do you get the angle? You get 2 theta equals, and what's the 0.02 times 2?
Would be that resolvability limit equaling this over here to 0.0432, right?
Well, what is
That's what I have
0.02?
over
What is
here.
0.021? That's not the resolvability. That's not the real.
Well, this is what we derive back over here using the very different and specific.
The angular resolution of the human eye is between, I can't read that, but 0.02 degrees and 0.03 degrees. Is that what that is? So you got the angular resolution of the human eye. Is that what that is? 0.02?
Sort of, right? We did exactly this. Again.
Okay, go down. Go back to, so you got that from, like, I guess. Okay.
All different ways to derive the same mathematical function that we're looking at from the beginning. Again, from the common wavelength, non-refraction interfering, one with the closest diameter to the human eye when squinting at the horizon. I'm going to keep saying it. People keep saying dumb shit in chat. Anyway, let's go. I love this one. So now, again, we've used the very specific criteria to derive different variables than the ones I'm showing you as the picture over here, right?
Hold on. No, I'm not getting that. Go back to the.
Right. So like this right here.
Okay, so go back to where you're doing the Rayleigh criteria calculation. Okay, all right. So I have 666 nanometers. Okay, so are we converting for nanometers and meters?
That's how we get radiance. So that's how we apply radiance to get our wonderful degrees, right? This is always
Okay.
a measurement of degrees at the end because it's just the angle at which things appear to disappear, right? The resolvability limit. And again, variable. Hyper dependent on circumstances. There's stuff about numerology in there, but like that's just happenstance as far as I'm considering. I'm just using the best, most average numbers we can. We can do it any which way it turns out. So we'll get to that.
Okay, so if go back 1 second. Let me see that again. Okay, so I get the 0.38, yeah.
Yeah. But
then I have to multiply that by 1.22. So according to Google, 666 nanometers divided by 2.16 meter or millimeters is 3.0833 times 10 to the negative 7th.
Again, this right here, right, is based upon specifically these measurements, right? So when we're talking about deriving the radius, the only two things we need is this.
Okay, well, I got a different number. Okay.
I feel like a lot of people don't want to hear me say that a lot.
I'm fine with you saying it. I just want to know why I didn't get the same number.
I feel like it's like grabbing a bunny out of a hat, like over and over again, though, and you're like, I don't really want to know the magic, so I'm just not going to do it, right? I'm going to let it fall. I'm just kidding. So where you want to go? You want to go back to the equation where we derive the radius? Do we get to the conclusion?
I got a different number than 3.762
for just the Rayleigh criterion basic ratio to start with.
Yeah, I got a different number. And
don't worry about that super secret personal eclipse calculator. That's not what I'm.
Okay.
Is that a linearized Haversine function I seen there?
No, that's for distance when we're messing around. I think it's this one. Wait, what are we doing?
Yeah.
As I'm very distracted, you keep messaging. I haven't read any of it, but it's been distracting every single time.
Okay, well, can you send me that picture? The pictures where you did the math.
I can do everything. Send you the document, the pictures, the RAR file, the website,
the
portal, the download. What do you want?
Okay, so I want the picture that we were looking at.
Yeah, I love that one. One of my favorites. Here you go. That's not it, but that's okay. I'm 50-50 copy and pasting today. It's all right. I get it next time, probably.
So sorry to interrupt, Mr. Shane. Is there a link I could send to my friend for all this stuff? Check it all out.
Yeah, absolutely. Here you go.
Okay, so send me that.
Everyone for everything.
Okay. and then I want the next. I want the Rayleigh criteria one that you did previously, and then the other.
It's one that just has like everything on it at once. It's really useful. But they're all really useful. So just like scanning through these at all would be great because they all describe different levels of the same thing. Like this particularly, it's just it kind of drills it home. Some of them are mixed and matched, but again, Rayleigh criterion. That's what I was looking for though. What'd you get a different value for?
I'm not sure, but yeah, I did. I was using that, but not that one. Just the one where you got.
Mhm.
I don't know that one there. That one. The colorful one. Yes, that one.
Yes, the numeral secret devil. Don't believe it because of numerology and it's all bunch of Satan one or something.
I don't care about the 666. That doesn't.
I mean, other cases I do. I might say it right or even use it, but in this one it's happenstance. Whoops, I'm a coincidence theorist. Anyway, this has been fun.
All right.
I
Yeah. Okay. I got to work. All right.
think I'm doing this all night. I think I definitely have. I got really far in eclipses before we started this, so that's going to be fun.
All right. I got to drop. All right. Take care, guys.
Always fun, dude. Later, man.
See you, Omni.
Yeah, dude. Thanks for being so respectful, Omni.
Well, that's fun.
That was like really edifying and enjoyable to listen to. You guys were both being super respectful. Nice change of pace.
He's such a good dude. Asking like real questions. Like, oh my god, it's so crazy. But like when that happens, though, it's like frustrating. I bet to have like all those questions immediately answered. I bet it kind of feels like being led, and I could be like, "Oh, piss the shit out of me." I'd be like, "Get to the point. Show me how."
Yeah, I mean,
you know.
well, yeah, he was clearly like trying to get to the bottom of everything and understand it all. That was great to
I
listen
was
to.
just saying, I'd be like, "Listen, I smell like I've already lost, and you just tell me what I've won." You know, like let's go. Let's get to the end of it.
Hey, I think I got one of the problems is the fact that the bottom of a boat or the bottom of the sun can be entering into the vanishing point that you cannot zoom it back into. I think it freaks Globers out that you can see the top part, but it doesn't matter how strong your zoom is, the bottom part is vanishing into the horizon, into the vanishing point. And I don't know if they're just like, nah, but that's how we see. That's what happens.
I mean,
And
I get it. That does kind of require its own explanation with separate visuals, but it is exactly a factor of how we see it happens all the time. In fact, it has to always happen that way. It couldn't happen any other way on flat Earth. Anyway, bottom of obstruction is specifically an optic function. And again, what we've done here, though, is like make that 8 inches per mile squared description that everyone's always agreed upon and applied it to a much more accurate degree to an optic function that exactly describes how we see non-linearly in all the places that we can apply it. Anyway, that's pretty much it.
But that's the hang up. They're like, no, that can't be. It's like a magic trick. Like actual reality, they feel like we're trying to tell them a magic trick they don't want to believe in, but we're just talking about what happens on Earth.
All the time, everywhere, yeah.
Hey, pull up the video that I private message or whatever because it's a water tower and it's 3.1 miles away. And I specifically in this example wanted something above the horizon to mess with optics. And there's a rack at the top of the water tower and it looks pretty big. And as I slowly zoom away from it, the top rack vanishes into the vanishing point. It's not down on the horizon, so it can't be tricky. And then almost the whole tower shrinks towards wanting to go away into the vanishing point. But then I zoom it back in, and it's just a really cool example if you want to stream it.
You got it, buddy.
Okay. I'm going to share my screen. All right. I'm pretty zoomed into this water tower. It's 3.1 miles away. And we were talking yesterday about the angular resolution or angular size of items and what optics do, what zoom does. And I'm using a P1000, and it has 125 times optical zoom, which is pretty great. So you can see a lot of detail in the top and just how big that looks. And as I back out away from that top cage looking thing, you'll see that you can still see it, but eventually it does shrink and it almost, you can't make it out. I mean, the towers, you can almost hardly see the tower. So with optics, you can bring towards, it's opening up the angle, giving you the ability to go farther in distance and gather more information in more detail. And that's, that's digital zoom, but that's the end of the optical zoom, so that's 125 times. So it's pretty awesome that this is available to us.
I like that video. Just be careful.
Yeah.
Let me make one comment. Just be careful when you're zooming back in. When you go further than what your normal eyesight would be, it's not a trick, but it's kind of deceptive, right? Does that make sense?
Yeah, I understand. I understand what you're saying, but let me ask you this real quick. So the whole like flat Earth hang up, or what's really been kind of tricky, is this boats over the horizon thing, and then us being able to zoom it back in. Where the Globers get frustrated is they're like, well, why is half of it missing when you're all the way zoomed in? And that's the whole thing I'm trying to explain, that at a certain point over the flat water, the half the boat is going to be disappearing into the vanishing point, where if you had a telescope or a camera 5 times as strong, you're not going to be able to resolve it because it is just gone.
I get your point, and I'm the same way, right? Like I post my videos and they have it full zoomed out and full zoomed in, right? Like, but it's good if you're doing a presentation or posting a video like that to explain, when it's fully zoomed in, that's the lens, right? That's the optical effect of the camera, not normal eyesight. When I zoom out a little bit, about 30 times, that's about eyesight, and then you zoom into 80 and 100 times, that's the lens again. Because
Yeah.
you don't want people to be thinking you're deceiving them, on purpose. Like, what I'm saying? It proves the point, right? It proves it better using a lens, but it's not where our eyesight starts.
Right. And the interesting thing is the sun setting on a flat Earth, as it lowers and lowers and lowers in the sky, it's the same thing as that water tower cage getting smaller and smaller. And then
Yep.
whenever what's that noise? And then whenever the sun is like half, obstructed, is what they'd say, it's just entering into the limit of the vanishing point. And so it's kind of crazy, dude, when you're looking into the reality of our realm and you're trying to like watch a car go off in a distance or the boat off into the distance, and you're zooming in as far as you can, and then it eventually disappears bottom up. The sun does the same thing, and us saying, hey, it's not going around a curved ball Earth, it's just not doing that. They're like, I don't believe you. That's just ridiculous. Of course it is. And that's the whole fight.
Careful, JT. When you put it that simple, you're going to trigger people.
Well, I mean, we got quarters on tables doing it.
No, I agree with you. I agree with you 100%. It's a very triggering thing, though.
But that's what
But
we're here to do, man.
no,
Talk
I know.
about
I just messing around, man. I agree. It's crazy. It's crazy. You put it really well right there. It's kind of just, in my opinion, one thing I've called it is just a cheap trick, right? Like what they do, extrapolating outwards to infinity from what we can see, and calling that an infinitely outward proportionate sphere.
This is why I think
Okay.
the people that go out and do their observations as Globers, this is why I think they're deceiving people on purpose, because there's no way you can go out and do your own observations, zoom it in and out and see what we see and not get what he's saying, right? Or tell someone it's different, right? It's not possible. That is not possible. That's why I think a lot of them are being deceptive in a way.
Well, I'll tell you, it is definitely an emotional roller coaster when you're trying to talk about this and, realize the deception of the globe. It bothers people. And I've tried to explain it this way. I've tried to say, I feel like both of us are in the stands at a magic show, and I know how the trick's done, so I can kind of see it, or I can kind of understand how this is happening. And my friend came with me, and they don't know how the trick's being done, and the illusion is completely like amazing. It's beautiful, it's baffling, and they like it. That's why people go to magic shows, is to be, awed by it. And now here we are, flat earthers, saying, "Whoa, bro." The heliocentric model is based on philosophy, and it was pushed by the Jesuits, and the Catholic Church was like, yeah, dude, let's do that. Let's go with that route. And all science was, created, or parts of science were created to line up with the theory, and math was invented to say this is what's happening. But here we are, flat earthers, saying, dude, we live on a plane, and optics are making it look curved, and it's not. And, again, that's the fight. But I appreciate all that everybody's doing to talk this out. I got to go on a run. I think it's epic. I think truth is worth pursuing, and this is fun. I was a Glober 2 years ago. Totally loved space. Totally believed we lived on a spinning ball Earth, and quote unquote, Mother Earth. They kind of like tied Mother Earth, ball Earth, to being nature, and I love nature. The mountains, the sea, anything outdoors, the woods. I love sunsets, sunrises, and the stars and such. And I've had to like let my mind turn to mush so that the lies would fall away and I could start studying out what is actually true in reality. And now I find it to be joyful and fun because I'm not like living under deception. But love y'all. Even if you think it's a ball, keep it up. Everyone's going to wake up, but we're just kind of early adopters of it.